Hello and welcome back to Learn It from a Layman. I am Carl Christensen, joined tonight by Matt and Tim, maybe. And that's not his middle name this time. That's literally, I'm uncertain as whether or not he's present. To be fair, I'm frequently unclear as to whether or not he's present, even.
He's like Schrodinger's podcast guest.
Yes, exactly. It's we'll see what happens, and it will be exciting. Okay, let's see. Tonight we're going to be talking about fluid mechanics, which, to be fair, I didn't know that was the name of like any type of scientific discipline until like 3 days ago, because Matt told me. So I won't be contributing significantly to the podcast, but I did want to say before we start, we got a lot of feedback about your robotics podcast, Matt.
Oh,
It's good. Someone said they won. They won a competition because of some of the insights you gave them in the robotics podcast.
oh, I don't know how to feel about that. I'm
Proud.
glad I helped somebody.
Proud, exactly. We're changing lives here.
Well,
We've also had a few.
congratulations to you out there, and I would give yourself a lot more credit for your hard work than you give to Learn It from a Layman for questionably accurate insights.
Questionably accurate insights, also the subtitle of our podcast.
Also a theme for this one. So,
Okay,
congratulations to you out there, robotic contestant.
Yes.
That's wrong. That would be like a robot that is a contestant. Contestant in robotics. There we go.
Yeah. So good job, Abby. Let's see. One last thing before we kick off with the fluid mechanics, Matt. We did start the last podcast talking about mustaches. I'm unclear on your opinion about whether or not mustaches are appropriate. What is your take?
They're okay. So, in general, if you think you look good with facial hair, you're wrong. And most people are too polite to tell you, and they just grin and bear it. I'm not too polite to tell you. I will tell you, your facial hair does not do anything for you. The one exception that I can think of is Santa, and that's it.
So a cleanly shaven Santa, yes, I guess that would look pretty sketchy.
Yeah. I'm not a. Yeah. Rarely do people pull it off well.
Yeah, well, Tim mentioned the '80s. Who there was that guy with the bushy mustache.
Yeah. So the best thing to come out of the '80s was, me, because I was born in the '80s. That was one of its few redeeming features.
Okay. So, not a mustache fan, and I think you're going against popular opinion by saying no facial hair, Matt.
I have the courage to stand up for what's right. Doesn't matter what the popular opinion is.
Okay.
My opinion is my own opinion, but I'm also correct in this one. So.
Okay, all right. So on that note, which I guess it's probably good that I shaved. I did tell people I might be wearing a costume, but then we had to delay the podcast because of my schedule for a couple days. So no costume and no mustache. So on that note, let's fluid mechanics, Matt. What are the basics of fluid mechanics?
Well, let's start with what is the basics of a fluid. What is a fluid? What makes a thing a fluid versus not a fluid?
Viscosity.
Actually, yes, that's one of the things.
All right.
But yeah, fluids are, the lay definition is for a liquid is a thing that takes the shape of its container. Right. In general, liquids are fluids. I can't really think of an exception. But air is also a fluid. Gases are fluid. Fluids are things that don't have any they don't have any strength when it comes to resisting shear forces. They immediately deform or change or move around it, as opposed to solids, which do resist shear forces. But yeah, for the purposes of our discussion here, you can think of fluids as being either liquids or gases. And fluids generally have a couple characteristics that define them. And the first one is whether or not the fluid is compressible or is non-compressible. Most liquids are going to be non-compressible fluids. Water, if you try to smush water down into a smaller ball of water, it's not going to work. Water does not really do that.
That's how we get heavy machinery, right? Hydraulics.
Well, even then, a hydraulic press works because the water in the hydraulics
doesn't compact.
The metal will give before the water compresses.
Right.
And so, water is a non-compressible fluid. Many liquids are non-compressible. On the other hand, gases generally are compressible fluids. You can take a gas and put it in a tank and put more gas in that tank until you have a whole bunch of it, and you've cranked the pressure in that tank up quite a bit. And so the reason that's important is because fluid mechanics, basically whether or not a fluid is compressible determines the equations and the principles within fluid mechanics that apply. And so as we talk about the different principles of fluid mechanics and all of that, some of them will apply to compressible fluids, some of them will apply to incompressible fluids. So that's one characteristic of fluids, is whether or not they're compressible or non-compressible. And the other one you mentioned is viscosity. Now, what is viscosity?
The viscousness.
Correct. So
it's when I think viscosity, can I get a layman?
Yeah.
So it's like the difference between just normal water, which is I don't know what the viscosity quotient is for water, versus like molasses.
Yeah. It's the layman term that I have just invented would be the liquidiness of the fluid.
Liquidiness.
Yeah. Now, and viscosity generally applies to liquids. You don't really have gases that are viscous. At least that's my understanding. I might be questionably accurate there. But anyway, yeah, very low viscosity means that it is super liquidy or runny. It will just flow and splash all over the place. And you can get super fluidity in very exotic conditions where you can even have a liquid that will run up the sides of its container because its viscosity is so low, it will just immediately coat whatever it's touching. As opposed to a viscous fluid, like you mentioned, molasses, that flows very slowly, or to some degree, even peanut butter is a super viscous fluid.
Teenagers before 9 a.m. No? Okay. All right. Well, I thought
I'm just going to ignore that.
Okay, perfect. Well, that's appropriate.
Yeah. But anyway, those are some of your main characteristics of a fluid. And if you know, depending on its viscosity and depending on its compressibility, it's going to react in different ways. The last one is whether or not it's a Newtonian fluid. And I'm not going to hit that one as much, but it's basically, does the fluid change its properties when force is applied to it? So if I press on the fluid or stir it or whip it, does its viscosity change? Or do its characteristics change? So one that I could think of A Newtonian fluid is something like water. I can press on water, I can stir water, it's still going to be water. A non-Newtonian fluid would be something maybe like pancake batter, where if you whip pancake batter, its properties change and it becomes a lot more liquidy. And then if you whip it way too much, it becomes too airy. And the way that it flows and moves changes depending on the forces that you've applied to it.
That's like
So,
the baking soda water too, right? Like when you
yeah.
put baking soda in water and
An even more basic one is if you stir a fluid, does it leave a lasting hole or depression behind it? Again, like brownie batter, really thick brownie batter. If I stir that, there's going to be that sludgy trough that gradually fills in, but it's still very noticeable and it's lasting. So that would be a non-Newtonian fluid. Again, they're governed by different equations that apply in different ways when we're trying to characterize a fluid and how it's acting or moving or reacting. And a disclaimer up front, I'm not going to go into a lot of the equations themselves that govern fluid mechanics, just because that's not really something that you can do in a podcast like this effectively.
Is it fair to say, I would, once again, layman, and not only just a layman, not knowing a few days ago that fluid mechanics was even a thing, my intuition tells me that all of the these formulas would be integrals and calculus type of stuff, because we're talking about curves
Yes.
moving, right?
Yeah, many of them are, especially when we talk about fluids in motion. Yes, you have to use calculus, and even then, well, we'll get to it. But yes, you're right.
Okay, cool.
So, but those are kind of the three characteristics of a fluid. Is it high viscosity, low viscosity? Is it compressible, non-compressible? Is it Newtonian or non-Newtonian? And based on those things, different equations are going to apply to it. Now, within fluid mechanics, there's two kind of broad branches of fluid mechanics. And the first one is statics or hydrostatics, basically a system at rest. And the other one is fluid dynamics, which is where you have fluids moving, dynamics, motion. Anyway, those are the two main branches. And we'll just go through and talk about some of the concepts in each one of those branches of fluid mechanics. Again, I'm not going to really be able to delve into the equations. A large part of being a good engineer in the realm of fluids, or scientist or researcher, is knowing which equations apply in which cases. And once you know which equations apply, well, then you can look it up, or have your computer fluid calculator select the appropriate equation. But for now, we're really just going to focus on the concepts rather than the math, because this is an audio podcast. And yeah, so
Good plan.
but yeah, let's start talking about hydrostatics, or static fluids. And all of this, I'm sorry. I have to back up one more thing. For both branches of fluid mechanics, there are some key assumptions that apply. And I'll go through them. There's four. The first one is that in the system that you're looking at, conservation of mass applies. So mass in minus mass out equals the change in mass. Mass is not created or destroyed. It can be calculated with the mass that you've added and the mass that has left the system, and that should give you the change in mass mathematically perfectly. Otherwise, mass does not, those are the things that apply to mass. Likewise, conservation of energy applies. Energy in minus energy out equals the change in energy. And conservation of momentum applies as well. And this is basically saying that Newton's laws apply to fluids. Every force that you exert on the fluid is met by an equal and opposite force back towards you. And then the fourth one is a little bit interesting. It's the continuum assumption. And the continuum assumption basically states that the fluid can be considered as a single continuous entity. Now, and what this means is we know that at a fundamental basic matter level that isn't true, because all matter is made up of finite particles and atoms and electrons and quarks or whatever. But for the purposes of fluid mechanics, we're going to say that, yes, all those little particles exist, but in terms of mathematical representation, we're just going to say it's one continuous blob of stuff rather than a collection of discrete particles that are moving around each other. And so that's the continuum assumption, and that applies, or we use that in general when we're dealing with the equations related to fluid mechanics. It's an idealized assumption, but we kind of have to do it, otherwise your calculations just become not a thing you can deal with very quickly. So with that, let's jump into fluid statics. And again, fluid statics have to do with a system that is in equilibrium with itself. So, and a system involving a fluid and a body in a fluid. In general, we're talking about pressures here. I have a body, a piece of matter, the hull of a ship, a submarine, whatever, and it's either floating on a fluid or it is submerged in a fluid, and nothing is moving. It's just right there. And I want to understand the interactions between the fluid and the thing that I've put in the fluid and the pressure involved when nothing else is happening. And so that's your field of statics. Now, fluid pressures are a little bit of a weird thing. And fortunately, a very smart man named Blaise Pascal, probably pronouncing that wrong, but he came up with, you have a Blaise Pascal, I don't know.
Right. Well, we'll call him blase. Sounds boring, right? Aren't things like blase?
Yeah, fluids is not boring, so that doesn't apply. No. Anyway, Blaise Pascal, I don't know. He came up with Pascal's law, which says that the pressure applied to the surface of a fluid is transmitted uniformly in all directions in that fluid. And this comes into play pretty heavily when you look at things like hydraulics. We've heard the term hydraulic this, hydraulic that. You mentioned hydraulic presses, and usually it's in the form of very powerful machinery that exerts very large forces on something. Well, fluids acting under Pascal's law, and keep in mind, not all fluids obey Pascal's law. But if you do have a fluid to which Pascal's law applies, then, well, you can do some interesting things with it, like hydraulics. Let's talk about that. So basically, Pascal's law says that if I have, consider a U-shaped tube, and I have a piston at either end of the tube, and the tube is filled with a non-compressible fluid, like water. Okay, Pascal's law would apply to that because, non-compressible fluid, that should be fine. If I press down on one of those pistons on that U-shaped tube, then the pressure is going to be transmitted uniformly all the way through that fluid and up into the piston at the other end of that U-shaped tube. So I'm going to press down on one piston and the other piston is going to rise upwards. And the key here is that the pressure that I put on the one piston is going to be the same as the pressure applied to the other piston. So if the pressure on my one piston is, say, 1 pound per square inch, then it's going to get me a pressure of 1 pound per square inch on the opposite piston. Well, no kidding, you might say. And I would say, but wait, there's more. Now, imagine your pistons are the same size. That's probably what you've been thinking. Well, if that's the case, then cool. You've made one piston go down and the other piston go up. Neat. Now imagine that the piston on the opposite side, the one that you're not pushing on, has 50 times the area of the first piston. Now I'm going to press down with a pressure or create a pressure, an additional pressure of 1 pound per square inch on my small piston. My opposite side piston is going to see the same pressure of 1 pound per square inch, but my area is 50 times as much. I have 1 pound per square inch over 50 square inches. What that means is the actual force, not the pressure, but the force that comes out of this is 50 times as high. So if I press down on my little 1 square inch piston with enough force to create 1 psi on that end, I'm going to get 50 times that force on the other end. So I can very quickly use hydraulics to apply incredible amounts of force through these pistons by not putting in a ton of force on the input end. This is how the brakes in your car work. So,
okay, I'm sure this works out, and I'm sure it makes this almost, to me as a layman, seems like it's violating the
yeah, it's totally cheating.
It's the opposite but equal reaction. Like you said, like,
yep.
Okay, but if I'm getting 50 times the amount of force coming out of it, is that just like, well, we're still satisfying Newtonian physics because
And so there is a trade-off here because the distance of travel is now very much different as well. If I want to push the far piston 1 inch upwards, I can do that, and I'm going to push it 1 inch, and it's going to exert enough force that it can lift a very large body that 1 inch distance, 50 times as much force as I'm going to put into it. The flip side is I have to press my piston through a distance that is 50 times as large. So if I want the far wide piston to go up 1 inch, I have to push my small piston down 50 inches.
Okay.
So that's kind of how it balances out.
Interesting. Okay.
Another thing, another implication of this is the maybe it was a real experiment. It's an interesting thought experiment. You can totally do this. You shouldn't because it ruins things. But the experiment of Pascal's barrel. Whether or not Pascal actually ever did this is a little bit up for debate, but whatever. Take a barrel, your classical barrel of water or wine or whatever.
I don't know how many people have a barrel sitting around, but continue.
Okay, well, it's an imaginary barrel. It's as imaginary as our listening audience. Now, you have your barrel filled with water. Okay. Now, take a large pipe and put it in the top of that barrel and otherwise completely seal the barrel. The barrel is now sealed except for this large pipe that is sticking vertically up in the air, 50 feet or whatever. When you start to fill that pipe with water, what's actually going to happen is your barrel is going to burst from the pressure. because the amount of water stacking up is going to put so much weight on itself as you build it up vertically and vertically, water weighing on water, weighing on water, transmitting all of that pressure all the way down to the sides of the barrel until it exceeds the shear strength, the failure strengths of the wood that makes up or the metal, or you can do this with a titanium barrel, and you'll quickly break your barrel if you put your pipe up high enough. But anyway, these are all applications of Pascal's law, that all of that pressure is applied throughout that fluid.
Right.
So fun stuff. So that's some of the stuff with hydrostatics. The other thing that we use hydrostatics for is to determine how much pressure a body in a fluid or floating on a fluid can withstand. So consider a submarine on the surface of the ocean. Now, there is some pressure on the hull of that submarine as it's cruising around on the surface. The water to the sides of the submarine presses into it with a certain amount of pressure. Now, as the submarine dives, though, the pressure increases because you have the weight of all of the water that is above that submarine and pressing on it. Well, how do you calculate how much pressure is really on that thing as it reaches an equilibrium at, say it dives down 50 feet or whatever? Well, this is where statics and hydrostatics come into play with some equations that I actually am going to talk about just briefly. But the basic thing is that you're looking at you're looking at two components to the pressure when you have a submerged body. You have a vertical component of pressure that is, on Earth at least, it's due to gravity. It's the weight of that water being pulled downwards by gravity. And that one's pretty straightforward. The equation is that the force in the vertical direction is the density of the fluid multiplied by the force of gravity times the volume of fluid that's above you. So however much fluid is there times its density times the acceleration of gravity, that's the force that's pressing down on you in the vertical direction.
Real quick question about that formula then.
Mm-hmm.
Layman question, might be very stupid. Fresh water and salt water, do they have the same density?
No, it's a little bit different. I mean, they're close.
Okay, but like if I have designed my submarine for salt water and it goes in fresh water, I guess.
Yeah, the differences are probably small enough that I don't know that you'd be really looking at something like that. But
okay,
different fluids do have different densities. If you design a submarine for operation in water, and then you were to sail it into a sea of mercury, for example, that might
as I frequently do.
Yeah,
A number of times I've sailed into a Mercury Ocean.
indeed.
Okay.
But that's just the vertical force that's pressing down on you. There's also a horizontal force that comes from that Pascal's law of that pressure being exerted in all directions. And you can think of it as, imagine a vertical plate underwater and how much water there is pressing down at the top of the plate versus the bottom of the plate versus the middle of the plate. Well, it turns out that if you just take the centroid you get of that plate, it averages out. And so the equation for the horizontal force is basically your pressure at the centroid times the area of the horizontal area of your submarine. So if my horizontal, or I'm sorry, It's not, when I say the area, it's the area of the submarine that is exposed to the horizontal force. It's actually the vertical projected area of the submarine. So if you think of a cube, think of a cube with a 1 square meter side, a vertical face. Well, that 1 square meter is going to see a certain amount of pressure, and that pressure times that area is my overall horizontal force. And anyway, these things, as you apply these hydrostatic equations, this lets you start to engineer your devices, your vehicles, your whatever that needs to operate in that fluid. And again, we're now talking kind of liquids. We're talking non-compressible fluids. We're talking Newtonian fluids. Different equations will apply based on the fluid that you're dealing with. If I designed my submarine to operate in water, it would obey a certain set of equations. If I designed my submarine to operate in brownie batter, a non-Newtonian fluid, I might have to look at some other equations. So, but anyway, that's just some basic points on hydrostatics. Any thoughts, questions, comments, concerns? Hydraulics is cool.
Hydraulics is cool. The only question I had was, okay, so you said horizontal force. Like most, well, aren't all submarines cylindrical?
Yes, not
So,
really. Modern day ones generally follow a cylindrical form, modern military ones. But no, a submarine can be whatever shape you want.
well, just I don't know how to calculate horizontal. A cube made sense when you gave me that example. I was like,
Yep.
okay, but
Think of the horizontal projection, or rather, I did it again. I said the wrong one. Think of the vertical projection that would be susceptible to horizontal forces. So if my submarine is cylindrical and has a diameter of 1 meter, pretty small submarine, but essentially I'm looking at a 1 meter high wall that force would apply towards.
okay.
I mean,
Okay.
there's more to it than that. I mean, again, learn it from a layman. We're questionably accurate. It
Questionable accurate
really has to do
insights.
with the centroid of the thing.
Okay.
But yeah, think of cubes. Just never design a submarine using our knowledge from learn it from a layman unless it's a perfect cube.
Okay, well, we should see a lot of cube submarines in the near future from all of our hypothetical listeners.
Yeah, exactly. So the other
Okay.
thing that you get with hydrostatics is one of the things that you might see day to day where hydrostatics applies is water towers. And water towers are what they are. They're giant tanks full of water that are raised up well above the ground. Because when you raise them up like that, the force of gravity allows them to apply a phenomenal amount of pressure, which then pressurizes the water system for the entire nearby area. And usually, your water tower drains during the day as it applies that pressure, and then they use pumps to refill it at night or during off hours. But because you always have that reservoir of water up there, you're always able to have a pressurized water system, which is why whenever you open a faucet in your house, water will come out. Isn't that cool? It doesn't matter if there's electricity or not, as long as the water tower is still there and still has water in it, exerting all of that pressure, you're going to have water available. So, all thanks
Okay,
to
so
Pascal.
oh, thank you, Pascal.
Yeah.
Pre-Pascal water towers didn't exist.
I don't know the history of the water tower.
It has to be
Somebody
pretty
may have
old, right?
figured it out because
We just must.
Pascal lived in like 16 whatever, but
Yeah, Seems like we probably had them before. We probably didn't understand exactly the physics behind them.
Yeah.
So like you described earlier, the U-shaped thing, the hydraulic system where I put in a pound of pressure on the one piston and I get 100 times as much force coming out, but the distance then has to.
No. So this is the key. You nearly got it right. You put pressure is force over an area, pounds per square inch. So I put a certain pressure on one end, I get the same pressure on the other, but I get a greatly higher force. And you did say
that's what I meant
force.
to say.
Yes.
So I got it right?
You got it halfway right. Yes.
Okay, I'll take it. Yeah. Halfway right. So with a water tower, we're doing the opposite, right? We're applying like a amount of pressure to a large object and then shooting small pipes off of it that then can carry water at that pressure for a long distance because there's a lot of pressure inside of that tank. Is that kind of the
you
idea?
could think of it kind of like that. I've
Because
got
I've always
this
been amazed.
giant column of water up there with a large amount of pressure, and so that large amount of pressure is going to diffuse all the way through my water system and keep that pressure up through every single faucet that's out there.
Right. Okay. Cool.
So with that, now that we've taught the world everything that they need to know about hydrostatics and pressure, should we move briefly to hydrodynamics?
Yeah, let's give it a whirl.
All right. Disclaimer up front, hydrodynamics is weird. Difficult.
Okay.
But this has to do with, as you might have guessed from the name, it has to do with fluids in motion, dynamic fluids, if you will. So we're talking about flows of liquids and flows of gases. And again, based on whether or not your fluid is compressible or incompressible or Newtonian or non-Newtonian or all of these things, different equations are going to apply. But with all of that, the same four fundamental assumptions that we talked about earlier, those do apply in our calculations: conservation of mass, conservation of energy, conservation of momentum, and the continuum assumption. So with that, there's a bunch of different things here. So some of the governing equations are the Navier-Stokes equations, and these govern, they allow you to attempt to calculate essentially, these are kind of hard to explain, and I apologize. If you have a viscous fluid, what they do is allow you to describe the forces and the force fields within that fluid as it moves. And okay, if you think of a solid object obeying Newton's laws of motion, if you push on that solid object, the solid object will start moving. If you apply enough force, it will apply a force back to your hand as you push on it. And it will very predictably move in accordance with your basic Newtonian equations, like force equals mass times acceleration. I push on some object that has a certain mass with a certain force, and I get a certain acceleration out of it. Okay, well, instead of pushing on a solid object, what if I'm pushing on a blob of Jell-O? If I push on that thing, it's going to deform around me. It's not just going to start moving in the direction, it's going to squish. And the Navier-Stokes equations are basically the equations that determine the forces within squishy things, squishy liquids.
Is that how that's written in the equation? The
layman terms.
Okay.
I have my jar of peanut butter. I push on the peanut butter. It deforms. I have a pool of molasses. I scoop it. I have oil. I impel it with a pump.
This would work like with a ball pit too, right? Like when I jump into a ball pit.
I mean, you could almost think of a ball pit as being sort of
Fluid?
fluid at a
Okay,
weird
fluid.
scale, but I don't know.
Oh, I will.
Yeah, but anyway, that's what these equations are for. They're kind of the analog to Newton's equations for force and motion when we're dealing with deformable fluids, squishy fluids, viscous fluids. And so these equations come to govern it. And I don't, again, I can't really go into these equations because even if I could, the Navier-Stokes equations, they are, you have to use calculus to solve them. They are all about changes in velocity and force fields, and you do have to make use of integrals, derivatives, all the things. And even then, you can only really solve them for very simple, very idealized cases where you have steady, continuous flow that is not, there's no turbulence in it. Anything past that, you really need a computer. And even then, when you get into more complex flows, like, atmospheric wind currents and things, it quickly becomes unmanageable.
Okay.
Sorry,
I'm
go ahead.
trying to, well, but this is from the beginning of the podcast, and I've been kind of thinking about it since then. And a squishy fluid, what is it, like a layman example of a squishy fluid?
Oh,
Brownie? I mean,
yeah.
what can you compact? Like, what can you?
Well, and squishy is perhaps the wrong word because it almost implies that you can compress it. The real thing is deformable. So consider Jello.
Oh, okay.
Jello, to my knowledge, Jello isn't really a compressible fluid. If you push down on it, it will make an indentation, but you'll see that matter kind of bulge up elsewhere, right?
Okay.
Yeah, so it doesn't compress, it maintains its same volume. And yet, when I press on it, it deforms. And so, I'm not going to get the same immediate force equals mass times acceleration the same way as if I was to press on a brick. Instead, I'm going to get deformation. And the way that it deforms and the speed at which it deforms is going to be a field throughout that Jello that changes. It will deform fast in the little portions of Jello that are close to my hand as I'm pressing on it. It will deform more slowly the deeper you go into that dish of Jello, farther away from the force that's being applied. There's a gradient to how quickly it's deforming. And because of those changes that you don't deal with in a solid object, you need the Navier-Stokes equations to define what the force state is at a given point in that fluid. And so if you're truly going to understand forces and pressures in deformable things like Jello, and a lot of study has been put into understanding Jello.
Way too much.
Yeah. But this also applies to all these other fluids. Now, I do want to jump over and start talking about just some of the things with fluid dynamics and in more general cases. Imagine water flowing through a pipe. There it is. It's just water moving. Even within that pipe, and even when we're dealing with something of as low a viscosity as water, there is a gradient to the velocity of the water in that pipe at different points within the pipe. And if you think of the cross section of water as it moves through it, what you'll find is that the water that is next to or touching the walls of the pipe, it's not actually moving at all. It's because of something called the no-slip condition. The molecules of water that are touching the metal or the PVC or the whatever of the pipe aren't actually moving. And that's what we call the boundary layer, and they're static. They don't move. It's just water molecules that are sitting there. And as you move in towards the center of the pipe, you'll find that the velocity of the water increases more and more. And it's not a linear increase. It's more of a parabolic change in trajectory. And so you'll find that the water that is moving fastest is in the center of that pipe, and the water out towards the walls of the pipe is, in the mathematical idealization, not actually moving at all. Now, the no-slip condition is kind of an assumption that aids calculations. Is it actually true? Well, kind of. There are exceptions to it. Certain in very, very low pressure fluids, like think air at extremely high altitudes where it's the density is very low. There's just not much air up there. If you have high altitude air moving through a channel, sometimes there's just not enough air there to satisfy that boundary condition. You'll find air kind of bouncing along the walls of your channel rather than sticking. Some fluids that are self-lubricating, like mayonnaise or high-fat things, they don't necessarily abide by the boundary condition. But in general, I'm sorry, the no-slip condition. In general, that's the no-slip condition is one of the assumptions that we make. And so your velocity profile, if you will, as you move through the cross-section of that pipe and the water moving at different points in that cross-section, looks like a parabola, starting at 0 on the outside and moving up to its maximum speed, following essentially a bullet-shaped curve toward the center. And again, if you really want to figure out the exact profile of that velocity curve, there are different equations that apply for different fluids, be they more and less viscous or compressible or non-compressible. Even the speed at which the fluid is moving. If your fluid is air and you're traveling at a reasonably normal speed, you're going to deal with a set of equations. If you're getting up to what we call transonic speeds, where you're approaching the speed of sound, you're going to deal with a different set of equations. If you've broken the speed of sound, you have another set of equations. And if you go up much higher and into the hypersonic realm, which is defined as really fast, it's not actually
you can quote us on that.
Between supersonic and hypersonic is not really super clear, but yet other equations apply in all these velocity regimes. And so a large part of understanding fluid flow and fluid dynamics is simply knowing which equations to apply in which cases, based on what's my viscosity, is my fluid compressible, is it Newtonian, how fast is it going, all of these different things.
So in order to study my cube submarine that I'm creating soon, and I want to use it to plumb the depths of the Mercury Ocean, I can start with the same. I can smart all of these things on a smaller scale, right? So I don't have to be creating a full-size submarine to study the forces. I could literally do this in my bathtub, and the same.
Well, assuming you can create equivalent pressure and flow conditions in your bathtub.
Oh, I can.
Okay.
You haven't seen my bathtub.
Can you simulate a lot of this stuff? Yeah, in different ways, you absolutely can. There is such a thing as a wind tunnel, which is used in aerodynamic engineering. And a wind tunnel is specifically designed to recreate the fluid flow conditions that your air vehicle is going to see at whatever altitude, at whatever speed. And when I say altitude, I'm really talking about the density of the fluid that it's going to be in. If you're at high altitude, you're dealing with less dense fluid, less air. If you're at low altitude, you're going to be dealing with a lot more air. One of the things that you run into in advanced aeronautical engineering is, and especially in things like jet engine design, is that the engines are specifically tuned to operate ideally with maximum efficiency in different densities of fluids that are moving at different speeds. And not all of those engines are going to perform the same way at different densities and at different speeds. Supersonic fighter jets are going to be tuned so that their engines operate ideally in those combat regimes that they're expected to be in. That might mean that they don't work super efficiently at lower speeds, normal speeds.
Mm-hmm.
But it's all of these characteristics are things that you have to design for when you're making whatever vehicle you're making to operate in whatever fluid you want to operate in. A high
Right.
altitude supersonic fighter is going to have different engineering considerations based on the fluid of that upper atmosphere than a low altitude supersonic fighter. And yeah, that's a thing. Likewise, a high altitude non supersonic airliner is going to have a very different engine setup than either of those fighters. And a private fun jet that's not designed to operate at super high altitudes is likewise going to have different, it's going to be designed for different fluids, essentially, different densities, different speeds.
It would seem that something like this, man, I don't know, isn't there a mission to Mars in the works somewhere? Um, that
Yeah.
the makeup of the Martian atmosphere has to go into like the same type of thing. That fluid that is going to be different than anything that we've seen that you've seen before, right? The atmosphere that they're leaving Earth from
Yes.
is going to be a different makeup than obviously the vacuum of space, and then the material that you're then flying through in Martian atmosphere will also affect your the forces will be different than what you've seen before.
Yeah, absolutely. And NASA did a really good job of planning for this when they sent the Ingenuity helicopter up with the most recent rover. So, for those of you who may not be aware, NASA put a helicopter on Mars. The helicopter that they put there had to be designed to operate in Martian atmosphere, which means a very different fluid regime than you would find on Earth. Imagine ultra high altitude on Earth. That's one, helicopters do not fly at ultra high altitude on Earth. That's not a thing they can do. And so NASA had to figure out how to do essentially that, operate in a atmosphere that was significantly less dense. And they did it. But if you brought that Ingenuity helicopter back to Earth, its efficiency would be very different. It's not designed to operate in the high density atmospheres of Earth. Could it fumble around and maybe get airborne? Well, probably. But it's certainly not designed or tuned or optimized for any of that. Likewise, a helicopter that was designed to fly on Earth probably could not fly at all on Mars.
Interesting. Okay.
Last two things I wanted to talk about with hydrodynamics, not hydrodynamics, but fluid dynamics, sorry, was two different types of flow, or rather two different flow regimes. Basically, you have laminar flow and you have turbulent flow. And imagine just water neatly flowing through a pipe in a straight line, nothing in the way, nothing perturbing it. It's just all going in that nice bullet-shaped velocity profile. That's essentially laminar flow. Now imagine whitewater rapids, where everything is churning and swirling and looking terrifying. Well, that's an extreme example of turbulent flow. And this comes into play in a number of different ways because the turbulent flow has different pressures and forces that it exerts on the bodies in it or around it than laminar flow does. This particularly comes into play with the design of things like airplane wings, where you want nice laminar flow as much as you can, but because of the shape of the wing, when the air goes over the wing, as it crests over the. I mean, we know what an airfoil shape looks like, right? There's a bulge on the top, and then it kind of tapers downwards towards the tail. Well, as it comes over the crest of that bulge, the air that's flowing over it, what if it just goes horizontally straight back? Well, then there's kind of a void on the upper surface of the wing past that bulge as it curves down toward the tail. And that void can cause major problems. You can immediately lose lift and your wing fails, and then you crash, and that's the end of you. And so you want to keep the flow going along over that upper surface of that wing after it crests that airfoil ridge as long as you can. And one of the ways to do that is to induce a level of turbulence, because that can delay what we call flow separation. Flow separation being that phenomenon when the air no longer follows the top of the wing, it just goes off after it crests that ridge. The fact of turbulent flow is not necessarily a bad thing. In this case, it can be used to keep your wing working. The fact of laminar flow is not always a good thing, but understanding when you want laminar flow and when you want turbulent flow and the different pressures that they exert on your wing is critical to making a wing that actually works. You want to make sure that you have a lot of pressure under the wing pushing up, and you want to make sure that you're not losing your airflow over the wing so that you don't just lose everything. And as you understand that, and as you understand how the principles apply, and as you understand all of the equations that I haven't told you about, you can start to design your wing to appropriately make use of laminar flow where you need it and turbulent flow where you need it, and optimize your wing. This is more or less what you kind of run into with the engines. How you optimize your wing is going to depend on the fluid that is operating around it. And the density of that fluid is going to vary with altitude. The speed of that fluid is going to vary with your speed. And so you have to tune your wing to operate in as wide a range as you need it to, based on whatever your requirements are. So when NASA needs to design a rotor blade to operate on Mars, they need it to work in a fluid of a particular density with the rotor moving at a certain speed, and they need to make sure that they have laminar flow as appropriate and turbulent flow as appropriate on different parts of the rotors as they're spinning around carrying that helicopter around. So I hope that made some level of sense. Again, this is an audio podcast. There's a lot of great videos out there, but you should listen to this first.
That's right. And after. And Tim, sorry,
Tim's here.
You are, yeah, well, he's the Schrodinger, Kim, you were the Schrodinger cat of this podcast, which now that you're here.
I believe the term is lurker.
So I think that means that the radioactive vial didn't break because you're not dead.
Well, this got weird.
I'm immune. I've been taking my radioactivity vaccines.
Excellent.
Oh, good.
Do you have any questions about fluid flow, Tim or Carl?
Well,
or
just
fluid
a
mechanics.
follow-up question on that topic. Say you made a band. which would be a more appropriate name, laminar flow or turbulent flow?
I mean, it depends on the band. Is it like easy listening jazz, or is it like, something that people would actually want to listen to?
That's right. I think Rammstein would be probably the right. We'll have to call them up for some advice.
Right.
Anyway.
Okay. So on that note, all right. Thank you, Matt. It's been, I think it was pretty insightful.
This is really just scratching the surface. I mean, fluid mechanics is there are significant college and graduate level courses that deal with this stuff. So this is just kind of intended to be a primer on some of the concepts. But
yeah. All right. Well, thank you, Matt, and whatever Tim provided for the podcast. And we'll be back again soon. I know we've had chemistry requested, so we've got to get chemistry done as soon as Tim just learns.
Every episode of our podcast didn't have chemistry. Sheesh.
Well, Tim, as soon as Tim learns the basics of chemistry, he'll teach us. So,
I could.
You could.
Yes.
Yeah. All right. Join us again in the next podcast, and we'll see you guys then.